We are still in the first chapter of the applied thermodynamics subject. We have started in this chapter to discuss about different type of the gas power cycle. I introduced you this type of cycle as one of the most common type of the cycle in the thermodynamics to generate power from the some energy source actually. And I have introduced you the air standard assumptions, which you need to use those assumptions to develop some idealized cycle actually to describe some machines or equipment which works based on this gas power cycle. Okay, I introduced you two different types of internal combustion engine. I told you we have two types of the internal combustion engine based on the how combustion starts inside the cylinder, and also based on the how air and fuel are introduced to the combustion chamber. Based on these two difference, actually, we have a spark ignition engine and compression ignition engines. And I told you that we have idealized cycle for these two type of the internal combustion engines, which for a spark ignition engine, I introduced you auto cycle. We have seen how we can calculate its thermal efficiency, what are the processes in this cycle. If you remember, I told you in the sparking in the auto cycle actually, which is the ideal cycle for the spark ignition engine, we had four different processes. You can see here we had two isentropic constant volume process actually, and two isentropic process. And we had to in during a constant volume processes, isentropic combustion, expansion, isentropic compression, and also heat rejection was in a constant volume process. Now let's see how is the diesel cycle, which is ideal cycle uh, for the compression ignition engine. Diesel cycle, ideal cycle for compression ignition engine. Let me just talk about that on PV diagram. I already show you how is the PV diagram for the compression ignition engine. If you compare these two type of the cycle, let me just show this schematic here. This is PV diagram. Imagine this is PV diagram for auto cycle. In auto cycle, we have something like this. And in diesel cycle, you can see the PV diagram for diesel cycle. What is the differences between these two cycles? If you notice here, the isentropic processes and also the heat rejection process in these two type of cycles are same. You can see here isentropic process, constant volume process, and this one, the heat addition process in auto cycle is a constant volume process, but this heat addition process for diesel cycle actually is a constant pressure process. So this is the main difference actually between these two type of cycles. But why we have this difference between these two type of the cycle? It is due to the difference between the main difference which we have between the combustion in the SI engine compared to a CI engine. If you remember, for the for SI engine, we said we have a spark plug, we have air fuel mixture inside the cylinder. Air fuel mixture will compress here, then we will have a spark by a spark plug, and combustion will start by ignition from the spark plug actually in the SI or gasoline engine. But how about the diesel engine. In diesel engine, as I told you, we have only air inside the combustion chamber. We call this combustion chamber the chamber which is between the piston and cylinder actually. And we have only air inside the chamber, and it is compressed with high compression ratio actually, if you remember. Then the temperature of the gas inside the cylinder is enough high, and we have injector here to inject fuel to the to inside of the combustion chamber. And due to the high temperature inside the chamber, when fuel is injected inside the chamber, it start to burn, and combustion actually will start due to the high temperature inside the chamber actually, high temperature air inside the combustion chamber in diesel. Now let's see why we have here constant pressure, and in the Otto cycle we have constant volume process. Because if you notice here in the uh, spark ignition engine or SI engine, we have air fuel mixture inside the chamber, and combustion just happen in a moment actually. Generally we say like that because we have spark here, and the fuel is all of the air fuel are already mixed and they are inside the chamber, combustion chamber already. But in the diesel engine actually, this fuel is injected during a time. As you can see here, you know, it start to inject, fuel start to inject the uh, fuel inside the chamber, and it takes a while to for the injection of the fuel. And this period actually will generate or the energy or thermal energy inside the chamber, or we can say we have Q in during this power struck in the compression ignition engine. As here, if you notice here, we here piston is in its top dead center. Here piston is in bottom dead center. So here, if you notice, when piston is in its top dead center, it means we have maximum possible compression at pressure inside the cylinder actually in this point, and the maximum temperature which we can have inside the cylinder is when the piston is in the top dead center. Okay, then after that, piston start to go downward, and we will have expansion of our system, or for the gas which is air inside the cylinder. This will cause reduction of the pressure. Due to expansion, the pressure of the gas will reduce. But in same time, we have a combustion inside the cylinder. And when we have combustion, the energy will release and temperature will increase. And this heat release inside the chamber actually, or based on the air standard assumption, instead of the heat release, we can say heat gain by the system during this process will cause increase in the pressure. So why pressure here is constant? Because from one side, the piston is going downward here, pressure should drop inside the cylinder. But from the other side, we have fuel injection to the combustion chamber, and we have burning of the fuel inside the chamber, releasing of the energy. So due to that, pressure should increase inside the cylinder. And in the ideal situation or condition, actually, this increase in the pressure due to the Q in is equal to the reduction of the pressure due to the expansion. So we can say that during the injection of the fuel inside the chamber, we have this constant pressure expansion process actually. Here we have expansion, the piston is going downward, the volume inside the cylinder is increasing. But due to this fact which I told you, increase and decrease of the pressure due to this Q in and expansion, then we will have a constant pressure process from state 2 to state 3 actually. So this is the main difference. Here in the spark ignition engine, heat release is in constant volume, but in the compression ignition engine or in the diesel cycle, it is constant pressure. Here, constant volume, auto cycle. In the diesel cycle, constant pressure. And on TS diagram, actually, we can show diesel cycle like this TS diagram from state 1 to state 2. We have a compression isentropic process from state 2 to state 3 or power cycle. Actually, we have Q in. Here is constant pressure. If you compare this with the auto cycle, this process from state 2 to state 3 is a constant volume process. From state 3 to state 4, we have an isentropic process, again, the expansion. And from state 4 to state 1, we have a constant heat rejection, constant volume heat rejection process, actually. So, first of all, it is good to know that if you notice, if you just know how is the auto cycle, then you can simply also understand the PV and TS diagram or the diesel cycle actually. When we have the maximum possible volume inside the cylinder, the piston actually is in its bottom dead center. And when we have minimum volume inside the cylinder, main piston is its top dead center. Thank you for your notes, actually. So this is the main difference, actually. What you need to know about the compression ignition compared to diesel, for the diesel cycle compared to auto cycle, is this part, the main important one. Same, you know, the isentropic compression is same in the auto and diesel cycle. Isentropic expansion is same. Constant volume heat rejection is same. The only difference here is this constant pressure heat addition process. And if you notice here, we have also another advantage for compression ignition engine compared to the spark ignition engine. It is, you know, if you remember, the compression ratio, the typical compression ratio for spark ignition engine was between 8 to 11 or 12, if you remember. But here, the compression ratio can be high, and it is typically between 12 to 24 actually. Why we can have this much of the compression ratio? The reason is here, due to the mixture actually, or the gas which we have inside the cylinder during the compression stroke actually. In the spark ignition engine, we have air fuel mixture inside the chamber. And if you remember, the reason why we have a limitation in the maximum compression ratio is auto ignition of air fuel mixture in high compression ratio, which will cause the engine knock. You know, air fuel mixture we have here inside the chamber. If we compress air and fuel too much, then temperature will be enough high to start ignition from, you know, different point from the cylinder, and we don't want that. We want to have the start of combustion from the spark, from just one point, then it distribute to whole cylinder. So high compression ratio in the spark ignition engine will cause auto ignition and engine knock. How about diesel engine? If you notice here, we have only air inside the chamber, so we can compress it as much as we want actually, based on the, you know, it's related to metallurgy, and we can compress air and increase its temperature much higher than what we have for the spark ignition engine. So generally, the maximum temperature of the CI engine is much higher than maximum temperature which we have for SI engine actually. This is due to this fact we can compress air without any problem. We will we won't have the auto ignition because we have only air, and fuel is injected to that hot air actually. So in compression ignition engine, the typical range for the compression ratio is 12 to 24 or even higher. And due to this high compression ratio, usually the size of diesel engine is bigger than or compared to the spark ignition engine, because we want to have more compression ratio. And later you will see why we want to have actually, why we are interested to have high compression ratio in the diesel engine. Later we will calculate the thermal efficiency of diesel cycle, and we will compare that with auto cycle as well. So what I told you about the difference also is mentioned here. Now let's see how we can calculate thermal efficiency for the diesel cycle like what we had for the SI engine or auto cycle actually. Same here if we write energy balance. Here again you need to remember that we have a standard assumption. Without those assumptions actually we cannot write this equation. These equations actually. So we have a standard assumption. We ignore the change in the potential and kinetic energy. Then if we write the energy balance for each process in the cycle, we can go and use the general equation. If you remember, always when we have a heat engine, we generally call this type of equipment which use heat to produce power, we call them as heat engine. So if you remember, thermal efficiency for each one of these heat engine is equal to W net divided by Q in. And Q in is what we give to the cycle, which is here the energy, thermal energy which comes from the fuel, and W net is the output of the engine, the work which we can get from the engine. So simply we can write 1 minus W net divided by Q in to calculate thermal efficiency. However, if you remember from the previous sessions, I told you that W net is equal to Q in minus Q out for this cycle. So if we substitute here, we will have this equation 1 minus Q out divided by Q in. We have Q in this process, we have Q out in this process, constant pressure process, constant volume process. So now if we can find Q out and Q in, we can calculate thermal efficiency for this cycle. Or we can, if we have Q out and Q in, or we have W net and Q in, simply we can calculate the thermal efficiency. But as I said before, it is not easy to measure this Q in. It is not easy to measure Q out. So instead of that, we can measure temperature in different states. So now let's first find an equation to calculate thermal efficiency based on the temperatures of the working fluid, which is air, based on their standard assumption here in the diesel cycle. So first, let's write the energy balance for this process to find actually Q in. In this constant pressure process from state 2 to state 3, we have Q in to the system. And also because, here we have expansion. And, here we have a closed system. If you remember from thermodynamics, we will have, a boundary work in these piston cylinder device. So simply we can write Q in minus WB out is equal to, this is the reasons to change in the energy of the system. Q into the system, WB out from the system. The boundary work which is done by the piston cylinder device on the surrounding actually. So Q in minus WB out, the reason to change in the energy. Or if you remember, we have this general energy, delta Q plus delta W is equal to delta E generally. See that energy balance relation. So here Q, we have only Q in W, we have only WB out of the system. How about delta E? Delta is equal to delta P, delta K plus delta U. Here, delta P and delta K are ignored. So the only change in the energy of the system due to these parameters, actually, due to the change in the thermal energy and the work, actually, is change in the internal energy. So you can write Q in minus WB out is equal to U3 minus U2. Energy of the working fluid at this state minus energy of the working fluid at this state. So U3 minus U2. So we have this equation for Q in. Now, if we restructure this equation, Q in, WB out, we will bring it to the right side of this equation. And about WB or boundary work for the piston cylinder device, if you remember, we had this equation, P dV actually, and we need to integrate that. But here, because we have a constant pressure process, we can write P, pressure also is constant here. So we can write PV3 minus PV2 actually here, or delta V here is delta V actually times P. So P delta V is WP. I hope it is clear for you because it is just from thermodynamics. So here is boundary work plus U3 minus U2. And if we restructure this equation again, we can write P3, we can write here P3 V3 minus P2 V2. Here, why we can write like this? Because P3 and P2 are same. P2, here we have a constant pressure process. So P3 V3 minus P2 V2 plus U3 minus U2. And also, you from thermodynamics, you know that H is equal to U plus PV. So here we have, P3, V3, here we have U3. So we can write H3, we have H3 here, this plus this. And for the H2, we have P2, V2 plus U2. So we can write H2. So we have enthalpy here. And if you remember, enthalpy actually is a combination, is a mixture actually properties of the internal energy and boundary work actually. So we can write H3 minus H2. And if you remember, for a ideal gas, we can write this equation, or for a gas actually, H3 minus H2 is equal to a constant, here we need to use constant pressure specific heat. Why? Because the process which we have here is a constant pressure process. So Cp times temperature at state 3 minus temperature at state 2. This equation also comes from thermodynamics. So H3 minus H2 is equal to Cp times T3 minus T2. So we have equation for Q in, here Q in and this equation. Now only these two equations are important for us, or only this equation actually, not equations. So simply, if we, delete everything here, what we have here now is only this equation, which is important for us. This equation, Q in equal to Cp T3 minus T2. So we have equation for Q in. How about Q out? We need that to write in this equation. Q out is in this process from state 4 to state 1. Rejection process, constant volume. Here, if we again write that Q delta Q plus delta W equal to delta E, we have Q out, here, but negative Q out. Why? Because Q out is going out from the system. And we don't have any work here. Why? Because we don't have any displacement. The volume is constant. So we have only Q out, negative Q out, because it goes out of the system. And U1 minus U4 is the change in the energy, or delta U actually here. So if we multiply both sides by a negative sign, finally we have this equation for Q out. Q out is equal to U4 minus U1. But here again, we have this equation from thermodynamics for ideal gas. Q out is equal to, or actually not Q out, U4 minus U1 is equal to CV. Here CV. Why? Because we have a constant volume process. And you know that this CV is a constant volume specific heat times T4 minus T1, temperature at state 4 minus temperature at state 1. So we have again another equation for Q out. You can see here is also similar to what we had for the Carnot cycle. So Q out is equal to CV T4 minus T1. Simply we can write here 1 minus Q out, Q in. We have Q out and Q out and Q in. We have already calculated based on the specific heats and based on the temperature at those 4 different states. Then we can write this equation. And K is the specific heat ratio, if you remember. So 1 minus, we just substituted Q out and Q in, which we have here in this equation. Then CV and CP will form the specific heat ratio. And if we bring out T1 and T2 from these two terms, we will have this equation. So if we have temperatures in these 4 different states, and if we have the specific heat ratio, this K depends on the type of the working fluid which we have here. If the working fluid is air, K is equal to 1.4, which usually we have only air. So K is usually 1.4, or it is given usually. So we have this equation. But now we need to introduce another parameter, which we call that cutoff ratio, or RC. RC, or cutoff ratio, is equal to the ratio of the cylinder volume after and before the combustion process. In other words, volume at this state V3 divided by V2. We call this cut-off ratio. Actually, it determines how will be the efficiency of the cycle. How? Here, if you notice, we have V3 divided by VT as a cut-off ratio. And from thermodynamics, actually, if you remember, we had equation for this to have a relationship between temperatures and volume. Actually, I'm not going to repeat here. In the examples also we will see that this cutoff ratio will shine in our equations. Actually, T4 divided by T2 and T3 divided by T2. Actually, this cutoff ratio will show in this equation. And finally, the thermal efficiency of diesel cycle can be defined based on this equation: 1 minus 1 divided by R power K minus 1 times RC power K minus 1, and so on. And if you notice here, 1 minus 1 divided by R power K minus 1. R is compression ratio. This up to here, it is similar to the Otto cycle. These terms is added due to this constant pressure process for diesel cycle. Actually. And you can see here the thermal efficiency of diesel cycle depends on this parameter R, or compression ratio, and also the cutoff ratio and extra parameters. How the thermal efficiency of diesel cycle change with these parameters? First of all, similar to the Otto cycle, by increasing the compression ratio, thermal efficiency of diesel cycle, as you can see in this graph, will increase. So in this graph, you can see on the horizontal cycle compression ratio, and the vertical one, we have thermal efficiency of diesel cycle. You can see here, as much as compression ratio is increased, thermal efficiency also is increased for diesel cycle. So it is same for both of the cycle. How about the RC, which is the other effective parameter on the thermal efficiency of diesel cycle? As you notice here, and also you can see in the, in the equation, as much as RC or is increased, the thermal efficiency of diesel cycle is reduced. You can see here RC or cutoff ratio is increased, 1, 2, 3, is increased, but the thermal efficiency of diesel cycle is reduced. So increase in the cutoff ratio means reduction in the thermal efficiency of the diesel cycle. This can be one interesting question. So increase in the cutoff ratio. What means the increase in the cutoff ratio or reduction of the cutoff ratio? Let me show on PV diagram of the diesel cycle. You can see here, cutoff ratio means V3 divided by V2. Increase in the V3 and V3, increase in the V3 actually means this distance will be longer, or the combustion process will be longer. Energy is delivered to this, it is produced in a longer distance or in the more period of time. So we have a drop in the energy which is released actually. We are interested to have a smaller, cutoff ratio or a smaller increase in the volume during this combustion process. And in a special case, actually, V3 and V2 will be equal, will be same, which in that case, we have a constant volume process. If V3 is equal to V2, cutoff ratio is 1. And actually, in that case, we have Otto cycle, not diesel cycle. So when RC or cutoff ratio is equal to 1 for diesel cycle, we have an Otto cycle, not diesel cycle. However, generally, we don't have this kind of process for the diesel cycle, due to that injection of the fuel. But imaginary diesel cycle with RC equal to 1 is an Otto cycle. And you can guess also from this, because we have a cutoff ratio. You can see here, when we have a cutoff ratio, the thermal efficiency of the diesel cycle actually generally is lower than Otto cycle. Thermal efficiency of diesel cycle is lower than thermal efficiency of Otto cycle. But it is important to notice this is valid when we have same compression ratio. If you notice here, the compression ratio is 12. This is efficiency of the Otto cycle. When the cutoff ratio, for example, is 2, this is thermal efficiency of diesel cycle. So you can see here that generally for the same compression ratio, this is important. For same compression ratio, thermal efficiency of Otto cycle is higher than thermal efficiency of diesel cycle. So why we use diesel cycle actually? Because you can see here in this graph, we can have higher compression ratio in diesel cycle, and in higher compression ratio, the efficiency of diesel cycle will be much higher. You can see here, even 24 or 23. And you can see here, it is even higher than Otto cycle. For Otto cycle, we cannot go beyond these 12 for the compression ratio. So you can see here the compression ratio for diesel cycle, because we can go for higher compression ratio, the thermal efficiency of diesel cycle can be higher than Otto cycle when we have higher compression ratio in diesel engine and lower compression ratio in gasoline engine actually. So this information, all of them are important. What is cutoff ratio for the same compression ratio? How is the thermal efficiency relationship between our comparison between the Otto and diesel cycle? And how is the effect of cutoff ratio on the thermal efficiency of the diesel cycle actually? And finally, actually, I already told you, this is the last thing which I'm going to tell you today. Up to now, I introduced you two different types of the cycle for internal combustion engines, Otto cycle and diesel cycle. Each one of them has its advantage and disadvantages. The advantage of the diesel cycle is we can have higher compression ratio than higher thermal efficiency. But in the but due to that constant pressure process, we have a drop in the thermal efficiency of diesel cycle. In same compression ratio, the thermal efficiency of diesel cycle is lower than Otto cycle. So in the modern realistic ideal engine or compression ignition engine, which we have today actually in the different type of the cars, we have dual cycle, not diesel cycle actually. How is dual cycle? Dual cycle means it is a combination of Otto and diesel cycle, like what you can see in this graph. The PV diagram for dual cycle is like this. The isentropic processes are same, the heat rejection process is same, just heat addition process or combustion process actually in the cycle from a state 2 to a state 3 is different for dual cycle. If you notice here, we have a constant pressure process here. We have a constant volume pressure, constant volume process from a state 2 to a state X. So this is for the diesel cycle. This is for Otto cycle. A combination of those two. How we can have this? First of all, we have a high-speed engine nowadays. So we can inject, when we inject fuel, actually, similar to what we have for the spark ignition engine, part of the combustion just happen in a moment. So we have a constant volume process. In other words, we have an increase in the pressure due to the combustion inside the cylinder, while the piston is almost constant volume. The piston doesn't move during that heat release, during that combustion process, the initial combustion actually. After that, when piston going down, with that higher speed, the combustion continue, and we will have a constant pressure process. So in same time, actually, in the combustion process, we have constant volume and constant pressure process. And this process actually will give us the higher efficiency compared to Otto and diesel cycle. And this is actually what we have for the diesel cycle. And nowadays, if you search out, so you can see the efficiency of diesel cycle is generally can be actually even 50%. However, the maximum efficiency which we can get from the spark ignition engine or gasoline engine is only until 30 or 35%. So this is also about dual cycle. In next session, I will discuss about the type of the power plant, actually the cycle which we have in power plant. But also, let me just introduce you this question, which I also will put in the column. You need to find the answer for that. Diesel engine operates at higher air-fuel ratio than gasoline engine. Why? You need to find the answer. Air-fuel ratio means how much air is combined with fuel or react with fuel inside the chamber. This is a fact, and you need to come out with the reason. Despite higher power to weight ratio, two-stroke engines are not used in automobiles. We have already discussed in previous sessions about that. The stationary diesel engine are among the most efficient power producing device, about 50%. The reason actually I just told to you, you need to come out with your explanation and understanding actually about the reason for this fact. And finally, you need to search and find what is turbocharger and why turbocharger is mainly used for diesel engine. This is also interesting. You can search and come out with your answer about this device. So by this we reach end of this session. Actually, next session we will continue our discussion about different type of gas power cycle.